We're going to be talking about a security environment here, which means not specifically about BPSec in particular, but a lot of the other things that exist around and underneath the work in BPSec. And a lot of this is going to focus on terrestrial network security because we are going to be implementing these things in an environment that already exists, in organizations that already have security policies, that already have infrastructure, that already have possibly entire departments that do what they do in a certain way, and they do their things for a certain reason, and you have to exist in their world, and you're not allowed to tell them to change their world for you. And then we're going to apply these things to challenge networks and DTN, and finally express a vision for one possible vision for a LunaNet security environment, and then talk about some ongoing and some future work. So it's not part of these slides, but Alberto had expressed some open issues during his discussion of operational networks and security, and we're going to solve all of his issues here with one possible set of security configurations. And this is about security practices for a DTN-aware audience. This presentation is not about DTN for security folks. And these slides are going to cover things at a topic level, but the paper actually gets into more details. So I'd refer you to the paper for very specific things about how things can fit together. So just as a background, generally, very top-level security information, there are already standards from NIST and other organizations about security strengths and equivalent strengths between different algorithms, different types of algorithms. These things are all well established and well understood at this point. And in terrestrial networks, scalable processing relies on a public key infrastructure, or PKI. And this is something that has evolved over decades at this point of operational experience and experimentation. And the table that's in here shows how there's some equivalent security between symmetric algorithms on the left and some asymmetric algorithms on the right. The main takeaway of this is that the required key material and the required processing of that key material for asymmetric security algorithms are many orders of magnitude slower and require more storage and more processing than symmetric algorithms. So, and symmetric algorithms themselves have better support for hardware acceleration, making the disparity even higher. So this is a basis of, we want to use symmetric algorithms for their speed, but they have limitations and scalability issues at a large network scale. So one part of that scalability limitation is the fact that in a symmetric key environment, purely symmetric key environment, there needs to be a key authority in order for the relying parties to have agreement on the key that you use to encrypt and decrypt, or the key that you use to apply a message authentication code and verify it. And this is something that exists in terrestrial networks and exists in space networks currently, but it limits the size and the dynamicity of networks because you start to rely on the key authority for things that the key authority doesn't even necessarily have visibility into, especially when talking about key rollover. And when we're talking about things like optical terminals, where you have multiple gigabit data rates and keys necessarily have an intrinsic limit. This is another thing that is a well-known property that has specific requirements from NIST, that you can only use a key for so much data. And the difficulty of a key authority is that you don't necessarily know what an actual end node is doing with those keys. And so it's a challenge you don't want to pre-compute so much, but then if somebody exhausts a key and you don't have a new key ready for them, then they're operationally dead because they don't have any keys to use. Now, on the other side, in a purely asymmetric environment, you can rely on the end entities to generate the keys themselves, And because there's a split between private keys and public keys, you have still an identity authority, but the operations of the identity authority are ones that can happen in an offline manner. And the benefit here is that you allow the end entities to have a certain amount of autonomy in what they're doing, and you can use the identity authority to moderate those entities, how the trust operates between them. And one other aspect of asymmetric and public-private environments is that you can actually provide another property called data origination that is not possible with symmetric keys. And this is where there are aspects of things like the point of data origination is to say that this entity and only this entity could have ever originated and signed this data. Whereas with symmetric keys, because you always need to have at least two people to know about it, and if there's a key authority, you have three people to know about it, you can't say that positively this piece of data came from this one entity, because at least two other entities know the key. So going back to the efficiency behaviors, the way that current protocols do manage efficiency is by establishing security associations between the peers. And the idea of this is that you spend some time to establish a security association, but one aspect of that that's derived are some shared secrets and some shared symmetric keys that you can then use as a way to optimize and provide high efficiency for actual traffic. And the way it's done typically is using an algorithm called Diffie-Hellman, which is a way that two parties can agree on a shared secret and then use that shared secret to derive keys. This technique is currently in use by protocols such as IKE and TLS, DTLS, and QUIC. This is the general state of the art of how terrestrial network security operates today. And this also results in known security properties. And there are derived security properties that are based on this that are well understood, that are well analyzed, and that have secondary effects that lead into things like NIST recommendations for key use and organizational policies about how things are supposed to operate. One other newly standardized terrestrial network protocol is called ephemeral Diffie-Hellman over Coze. And what this is doing is it's actually decoupling the security aspects of key exchange mechanism, authenticated key exchange, from transport. And what I put in the slide are two pictures. The first one represents a key exchange and security association negotiation for IPsec IKE, and the second one is a negotiation for ad hoc. And what you'll see is that they are very similar in that they both have kind of wrung out all of the extraneous exchanges and unnecessary delays between the nodes. And so they're functioning very similarly, but IKE is necessarily very tightly coupled to IP and IPsec. And the reason for ad hoc existing in the first place was for constrained devices. They wanted a way to do the same kinds of key negotiations and get the same security guarantees, but in a way that's not as tightly coupled to IP. And well, later on, we'll talk about this, but we get a benefit from this because the constrained devices groups have already done the work to separate these behaviors. And there are ways that we can take advantage of this existing protocol and embed them on top of BP and BPSec and not have to reinvent security aspects and not have to end up with different types of security properties. One other aspect of this that is purposely designed into the protocol is the ability to have this external authorization, EAD, that can be used by different embedding applications. And one possible way of using this is for negotiating properties about BPSec. Getting back to the PKI aspect of things, there are lots of possible key distribution mechanisms that have been experimented with, that have been tried operationally. And the current best practice on terrestrial networks is to use PKI with X509 certificates called PKICs. And PKICs has existed for a while now. It's more than 25 years, probably approaching 30 years of PKICs being in existence. But the uptake of PKICs and the ability to use what is now called web PKI and email PKI really depends on processes of certificate authorities. PKICs itself says these are the menu of possibilities of what you can do with these certificates, but it takes something like what's called the CA browser form, which has now existed for about 20 years, to really negotiate down not what is possible, but what is necessary to do as a CA. And this type of thing is really important because it constrains how CAs can operate, and it constrains how relying parties can use those CAs, so that everybody's in agreement about what things mean and everybody's in agreement about how things operate. And this is above and beyond the protocols themselves. In the DTN domain, these haven't really been, or in the non-terrestrial networking generally, these haven't been worked out in the same way as what the CA browser form did. And the reason for that CAB to exist in the first place was a very difficult period of time when it was a little more Wild West, where CAs were operating in very different ways from each other without certain guarantees. And what it ended up with was serious security situations where I trust 10 CAs equally, and 5 of them are very well behaved and 1 of them is very poorly behaved, but I don't treat them any differently, and I don't have any stamp of approval on any of my processing. So my one badly behaved CI will basically pollute the ecosystem and cause a bunch of spoofing websites to steal people's credit card information, for example, which is very bad PR. I'm not going to get into details about the PKI, but the concept is that you have separate certificates with separate profiles for separate purposes, and the CA is the critical part of all this processing, because the CA is the, I'll talk about it in a minute here, but the CA is the organizational structure that you have to trust, and your trust flows from the certificate authority down to the end entities. So I trust the entity because the CA trusts the entity, and I have to implicitly rely on the CA to be well behaved. So zero trust architecture is something else that is worth having an eye for in this kind of security environment, because the point here is to say that I can't allow my security to be implicit or transitive, in that just because I received information from a peer over a trusted channel doesn't mean necessarily that that information itself is trusted. So the point of the zero trust architecture is to say, just because I receive something from a network that I trust, or I receive something from a radio net that I trust, doesn't mean that at the higher levels I should trust that information, that I have to do my own authentication at each layer. And authentication in existing terrestrial networks still can happen on individual datagrams. And because of historical reasons, this is how email security, called SMIME, operates. Back in the time when email servers were a lot less well connected than they are today, the email might take a few hours or days to get from poorly connected subnetworks all the way to the destination. So email already operates in a security environment or a security model where delays are necessary and have to be accommodated. And so authentication can also come from a security association indirectly, meaning I perform some early authentication to establish a security association, and then I rely on that security association to amortize the cost of that authentication for each individual datagram. And this is how TLS and DTLS, Quick, and IPsec all operate, that they do a heavyweight operation up front and then use that to efficiently process traffic. But this relies on that security association, whereas things like SMIME, individual datagram security, can't do that. It's a one-shot operation that has to be processed in isolation. And then it's important, this is another NIST requirement in key management, is that you don't use the same keys for different purposes. So traffic authenticating keys are treated separately from traffic encryption keys or other key purposes. And the picture on the right is just showing that receiving datagrams in a secure environment, each datagram itself has to be treated independently from the other. Just because I received and handled a valid datagram that I got from my radio doesn't mean that the next one down the line is going to be trusted. It could be that the next one down the line is forged. It could be that it's replayed and I should ignore it. It's still valid, but somebody's trying to attack me. So each piece of information that comes off the underlayer network needs to be authenticated separately. Separate from the key management aspects of things, there's an important part of security that's authority for naming. And this is something that Alberto brought up, which was how do you trust that an application actually is supposed to operate with a certain endpoint ID? How do you trust that a node is supposed to have a certain node ID? And the way this works in the PKICs is there's something called a name constraint, and there are things called subject alternative names. And the idea is that end entities have names, and CAs can have name constraints. And it's a way of delegating authority to say, as in the example picture here, my root CA is trusted to name anybody, but they delegate to two other CAs. You can only name A, B, and C, and the second CA, you can only name D, E, and F. And this is something that's built into the PKICs, but this relies on the fact that there's an agreement of how name constraints are processed and how subject alternative names are validated against names constraints. It's very nuanced, and it requires specific, not just concepts, but it requires specific processing algorithms that everybody has to agree on. And the benefit here is that there's no relationship, no necessary relationship between CA hierarchy and naming hierarchy, in the sense that in a federated environment, you can have multiple organizations that have allocated names, all delegating their names to the same CA because they want to share that infrastructure. And vice versa. A single CA can be delegated a portion of an organization's namespace because that's convenient to do. One important aspect, and it's in the title of the paper, is autonomy. And what autonomy means in a security environment is the ability for edge nodes to direct their own detailed behavior and distribute the functions to the edge as much as possible. And it allows the interior of a network to be ignorant about why edges are doing what they're doing. You distribute the functions so that the edge nodes, for example, will do certificate renewal, or will do key rollover, or will do security association upkeep at the time that they need to. The interior of the network doesn't need to care about when they're doing these things, or doesn't need to care about if a node chooses to renew their information or upkeep their security associations early, because they know that their connectivity is going to be down at a certain period of time, and so they want to renew that information ahead of the connectivity loss. That's something that the interior of the network and even the security orchestration doesn't need to care about, because it's the edge nodes that know their situation the best, and they have the best information to be able to do things autonomously. So getting into the challenge networks and the DTN aspect of things, I'm not going to touch much of the background here, but we already have sort of environments and architectures and understanding of what these challenge networks do. So we're going to jump right into how do we expect that we can implement security in a more distributed way. One aspect of this is we're expecting that there are going to be different enclaves of nodes. And this is because of organizational reasons. This is because of physical, geographic reasons. This is because of topological, administrative reasons. There's a lot of reasons why there might be different clusters or enclaves of nodes. And there are going to be significant delays. There are going to be significant throughput restrictions between these different enclaves. And there also might be multiple connectivity between them with different schedules, with different purposes, different qualities of service, and different access allowed or disallowed. So this is a basis of how we're going to integrate this security. One other thing that's kind of a keystone of some of this discussion is that we can treat these environments as if there are going to be islands of IP. This is something that doesn't exist right now, as far as I know, as official policy or any official architecture, but the implementations that are currently in development seem to be based on the fact of they're reusing commodity equipment or protocols for LANs or WANs to be used in these different enclaves. The NASA CLPS is experimenting with what's called the tipping point project, which is to use 3GPP equipment, and that necessarily is going to establish IP networks. Whether or not the IPs are used by the end nodes or end entities is not important, as much as there is IP connectivity within these enclaves. And we don't need IP outside the enclave, but we can benefit from using IP within the enclaves. So what this is going to allow us to do is make use of pre-existing and well-understood security tools and protocols within the enclaves, so that we're not just taking the properties of these existing protocols and tools, but we're possibly taking the tools and the protocols themselves within an enclave. That's an important part of things, because within an enclave, there's likely to be higher bandwidth, there's likely to be lower latency, there's likely to be more continuous connectivity. So on the next couple slides, I'm going to talk about how putting these two things together, this pre-existing set of tools and protocols for terrestrial IP networks, fits into the current LunaNet architecture, and one way to advance things to a point where you can actually start doing detailed experimentation or detailed prototyping on some of these things. And one aspect of this, like I talked about at the very beginning, is that a real LunaNet security architecture is going to need to integrate with the existing organizational tools and policies. It's going to need to rely on key management and identity management that is not under the control of necessarily the DTN administrators. It's something that already exists in these organizations, and it has to fit into that environment. And one thing that this also enables, and in some cases will really benefit from, is cross-agency support. This is something that is mentioned a little bit in the paper, that there doesn't really exist right now that same kind of CA browser forum for space internet working and security in particular. So this is something that needs, it's an area that needs investigation and work, but it's also something that sort of falls under the same kind of purview of the the CCSDS cross-support area that already deals with how do agencies interoperate organizationally, how do they interoperate at the level of data sharing and things like that. So this slide covers a few existing technologies that are discussed in a lot more detail in the paper. I'm just going to briefly go through them. But the interesting part is just that the current Internet of Things and constrained device environment really already mirrors some of the DTN architecture. They don't explicitly do things for the same reasons, but they're dealing with small devices with small memory footprints, with low processing abilities, because of power limitations, intermittent connectivities because of radio limitations, with low throughputs. And so we can take advantage of and share effort with these other groups that are already doing work in these areas. And some examples of this is something that the paper covers in more detail, but we already have ways to do public key certificate enrollment using techniques of what's called the IEEE 802AR. That is a way for enrollment to happen between organizational domains that have specific trust between each other, but it lets the devices do things somewhat autonomously. Because in data centers where you have device vendors who are different from the network operators, who are different from the end users, these things already have to exist. The ACME protocol is something that already exists and is widely distributed. The Let's Encrypt service of, I forget what internet organization that's been running for about 10 years now. I have the figure in the paper, but they're servicing something on the order of, I want to say 50 to 60 million certificates per year. It's some incredibly high number. And these things are already built to scale up enormously, and they're built to be distributed. This is something that's still in development, but how do PKCs get distributed? Well, there's the possibility of leveraging BP multi-point messaging. There's a possibility of using something like DTKA as a way to distribute these things across a network. And ad hoc, like I discussed before, is a way of doing SA establishment by binding it to, say, BP7, using without touching the ad hoc protocol, without modifying the security properties. So the autonomy that I'm talking about here is separated between a higher level goal and a lower level set of mechanisms to achieve that goal. So in this case, one goal is provisioning a node, and then the autonomy is allow that node to use shared protocols to figure out how to establish themselves in a network. The next goal is enrolling in a network where you have the device provisioned, you know where it's going to be, allow the device to figure out how to bootstrap itself into a network, how to establish trust between end entities based on trust derived from the certificate authorities. Another piece of autonomy is the upkeep of certificates, the upkeep of security associations. Autonomy in this case means allowing a node, an end node, to decide when is the best time to renew based on all of the available information that it has that the central authority might not have. And then monitoring is an important aspect of this, which is when you have autonomous systems, it's important to be able to make sure that they're doing the right thing. But what this means is that it's not a closed loop kind of feedback involving central control. What it amounts to is configuring the goal on the end entities and then monitoring that they're doing the right thing and they're doing the thing that that falls in the envelope of what is reasonable. So you don't prohibit or specifically authorize activities, but you monitor what's happening and then allow organizations and administrative domains to figure out, is somebody misusing my resources? Is somebody behaving in a way that I don't think is correct? And there's a life cycle that's described in more detail in the paper, but the idea is that this security environment needs to cover everything from device manufacturer, and device here is in the most general sense, because this is something that happens with equipment even before it exists as a node. At manufacturer, there is no node yet. You still haven't assigned and authorized names. So starting from manufacturer to provisioning means it has a name, but it's not enrolled in the network yet. Enrollment means now that you actually have the device in the environment that it's going to operate, how does it trust other peers in the environment? How do those other peers trust it? The operations in this case means real network operations, passing actual application data. Up until step 4 here, you are not in a position for an end device to actually process and transport data. You're still trying to get onto the network. But once you're onto the network, it's important that there's certain upkeep activities that have to happen to keep you in the network. And then finally, deprovisioning and possibly reprovisioning is important to consider, because these space missions have a certain design lifetime, but then they are liable to have margin and exist past their design lifetime. And that means that where you had some node, some mission that was originally focused on science, because of needs in the network, might transition to be more of a data relay. It might be that some sensors fail, but some of the radio equipment or optical equipment lives on, and so you can't operate science, but you can act as a data relay. And maybe that means that roles have to change, or names have to change, or even possibly operators of a device change. And so there has to be a way to consider changing identities of a device while it's in service, without having to take the thing back to Earth, because that's not possible for a lot of devices. So the main takeaways from this are that these all exist as near-term paths to trying to integrate DTN security into a larger enterprise security environment. And one thing to consider is that the evolution of these security mechanisms on terrestrial networks didn't originate pristine from a committee. They have been hard won over many, many decades, and a lot of failures and a lot of bad behaviors that led to the current set of good enough behaviors. And then finally, I have some links to some work, and these are all referenced by the paper as well.
I'd like to use a question. Every once in a while, I wake up and say, hey, today's a good day to build what kind of security protocols and what's happening in the world. And so 45 minutes later, after I've logged into my computer with 3 passwords and RSA token tag, I find emails from 47 different people that have all different ideas how to do security for Mars, for LunaNet. I talked to a fellow at headquarters once. His opinion of security is, well, we're going to figure out how to do it for LunaNet. And then once NASA's figured out how to do security for LunaNet, then we'll throw that over the fence to CCSPS and let them worry about the rest of it. And so then I go to the CCSPS crowd, and we've got a number of CCSPS folks here. There's system engineering architecture working group who's trying to do a security architecture, pretty much independent of all the rest of the working groups. Then we got Howie and the security working group, CCSPS. And then we got Eric Barkley and the cross-support transfer service working group. And their main focus is how do you tell the PSN what passes you want and how to pass the information back and forth to establish connections and remember service providers. They don't think about security much. You know, you have the famous DTN system. Building company. How do we wire all this stuff together and try to come up with recommendations and get recommendations like yours out in the world so we're not constantly herding cats?
The how, I don't know exactly, but the basis of what's here and what's in this paper is to say, don't try and invent things from scratch. Don't try and do things anew, but try and figure out how to fit the existing things into your operations. So that's that's the best I can say as far as.
You need to make Ed Moran
Terrible idea. Terrible idea.
It's not so much a question, but maybe a response to that. I think the CCSDS section is the wrong forward for that. So I mean, we are trying to get IoT security working, start with the focus on the applications. And I think there's also a subvertical one, security, which I don't know where it's from. I think this is really where get this work in. And that we also do not just need to get the DTN people or security people, but get people into operating security. This is going to be a difficult part. Because these are the people that later tell you, we cannot do this because of whatever. Yeah. I mean, the difficulties of setting. So I still have hope that IoT things start soon. From that, I guess we would get more requirements for standard integration.
And that is.
Yes, yeah. I mean, there's a governance committee thing coming out, but there's also the idea of a dedicated security work. I think in terms of reference, we should focus on communication. But I think it's still in the progress of
part of a side effect of at least some of these recommendations is to make use of the existing things in a way that it doesn't, in some cases, it doesn't even require new tooling, but just new ways of using the tooling, or what I think falls more into the kind of cross support thing, which mimics the CA browser forum, which is just get enough people to agree to it that it becomes a useful thing. But that doesn't prohibit, as a starting point for prototyping or experimentation, a couple of end nodes to start, agreeing, and then from there building out. The benefit of the distributed aspect of this is that it doesn't have to be like whole cloth all at once. Everybody has to agree now. It can be incremental.
Do you have any specific recommendations for interoperability testing? For specific security. So let me know part of the DTN program.
Do you have a charge code for that?
Yeah. I mean, the only